Okay, so we are now in section 1.1c. This will have a lot of writing in it. I'm just giving you fair warning, but there's really no way around it, and you need to know these limit rules. In fact, big old hint, hint, on the first chapter test, there is a couple questions that require these rules, so make sure you know them. Okay, so if you're taking a look inside this rounded rectangle right here, you'll see that there's a couple definitions there, but I want to explain them by drawing pictures. So for the first one, the limit of a constant function. So let's draw a constant function. Okay, so a constant is literally just a horizontal line, right? This is pretty much the same thing as drawing y equals 5 or y equals 2 or y equals -7, right? It's just a horizontal line, a constant function. All right, so if we are approaching this value here, which I'm calling c, and by the way, I should probably name that constant function k, right? I know, it seems weird not to use the letter c for constant, but for whatever reason, we use k. As I am approaching c from both the left and the right, you can see that I am approaching k, right? The entire function is k. All right, next, the identity function. So let me make sure I draw what the identity function looks like, which is f of x equals x. It looks like this. All right, so if I said, hey, this is c, and I'm trying to approach it from the, right, here's c, the left and the right, this has to be c, because no matter what number you plug in here, it's the number that comes back out. Okay, so let's get down into these rules. All right, so first thing, right down here, it's saying that the limit as x approaches c of function f is equal to L. All right, and then it's also saying that the limit as x approaches c of a different function, g of x, it equals m. All right, so the sum rule is exactly what you think it's going to be. It's going to mean adding. So let's write down our notation. The limit as x approaches c of f of x plus g of x. Okay, so the sum rule, in essence, is telling you that the limit of the sum is the sum of the limits. In other words, I can separate it. Maybe I should put parentheses so you can kind of understand what I'm talking about. Instead of doing the limit of the sum of the functions, I can take each individual limit. So that means L plus M. All right, so now the difference rule is exactly, again, what you think it's going to be. It's the limit as x approaches c, but this time we are subtracting f of x minus g of x. So the limit of the difference is the difference of the limits, which looks like this. The limit as x approaches c of f of x minus the limit as x approaches c of g of x. L minus m. All right, so most of these are going to be literally what you think they're going to be. The limit as x approaches c, and since it's the product rule, we're going to multiply those two functions together. Okay, so the limit of the product is the product of the limits. All right, I'm hoping this makes sense. Again, if there's questions, write them down. I will answer them in class. Okay, quotient rule. It means if I'm doing the limit as x approaches c of f of x divided by g of x, then I can do the quotient of the limits. So the limit as x approaches c of f of x divided by the limit as x approaches c of g of x, which would be L over m as long as m does not equal 0. Okay, so the constant multiple rule, let me write this one up. Means if I'm multiplying a constant times a function, I'm going to move that over there because I'm running out of room. All this means is it's just the product rule, really. It's the limit as x approaches c of a constant times the limit as x approaches c of the function, which gives me this one. The limit of the constant is the constant, and then the limit of the function as x approaches c is L. Okay, and so then the final rule, the power rule, looks like this. The limit as x approaches c of a function that is being raised to a power. Okay, so notice in that what I just wrote down, the function is being raised to a power. But I can change that so that it's just the limit as x approaches c of the function where I'm doing the entire limit raised to the power. So in this case, this would be L raised to the p. All right, so now that you have all the rules, and again, you will be required on the Chapter 1 test to use those rules. You may not skip over the middle step, all right? I've said it twice now. Let's see now if I can do this limit down here. All right, so the first thing I'm noticing is that I have a sum and I've got a difference. So I'm gonna break this apart into 3 separate limits. The limit as x approaches 2 of 3x squared plus the limit as x approaches 2 of 9x minus the limit as x approaches 2 of 7. Okay, so now that I've separated it using the sum and the difference rules, this first term right here has a couple different things going on. There is a constant being multiplied in front, so I can use the constant multiple rule. And then there's also an exponent. So I'm going to use 2 rules at once. It'll look like this. 3 times the limit as x approaches 2 of x squared. All right, for the middle term here, this 9 times this x, again, is a constant times a variable. So I'm going to use that same rule that I used on the first one. 9 times the limit as x approaches 2 of x. And then on the last one, the limit of a constant is a constant. Okay, now if you look up in the box up above, I know what this equals, and I know what that equals. So this ends up being 3 times 2 squared plus 9 times 2 minus 7. Okay, now what I'd like you to do, and this is very, very important, so if you don't get this, please write something down and ask me about it when you see me. This step right here is unbelievably important because if you look at this line and you look at the original problem, you can see that all I've actually done is taking that 2 and done direct substitution. Direct substitution. Direct substitution is always your very, very first line of defense. If you see limit notation and you are asked to figure out what the limit is, the first thing you always want to try is direct substitution. Okay, now moving on. There's some words at the top of this page. I do kind of expect you to read them, but I'm not going to read them to you. okay? But you do want to read a little bit or focus on this part, okay? Because direct substitution isn't always going to work. Yes, it's what you want to do first, but when it doesn't work, you have to have something else to fall back on. So let's take a look at example 6, and there's some parts to it. All right, so on part A, I'm gonna plug in -3 in for all those x's, and I'm gonna see what happens, okay? So if I put -3 in for x squared, I get 9. If I put -3 in the next term, I get +6. And then I bring down the -15. And on the bottom, when I put -3, I get 9 minus 9, which ends up giving me 0 over 0. Okay, that is called the indeterminate form. It's really important. Indeterminate form, right there. Okay, so there's a bunch of different methods that you're going to learn to try to take care of that. Okay, the first one, and probably the easiest one for you, is going to be factoring. So let's rewrite the limit notation. All right, now the top is a trinomial, and it factors to be x minus 5 times x plus 3. And the bottom factors to be x minus 3 times x plus 3, because it's a difference of squares. And you can see that these cancel out. Okay, so once I've factored and I canceled, now when I try to do direct substitution, I get a different result, right? On the top, when I plug in that -3, I get -8. And when I plug the -3 on the bottom, right here, I get -6. And this reduces to 4/3. That's the limit. All right, so let's take a look at B. Now, again, I'm always going to do direct substitution first. And I probably should use some correct notation here so that you get in good habits. So if I'm going to do direct substitution on the top, it looks like this. And I get 0. And if I do direct substitution on the bottom, I missed a 5. There we go. That gives me a 0. So that's the indeterminate form. 0 over 0 or infinity over infinity is the indeterminate form. So the method I'm going to use on this one is I'm going to multiply by what's called the conjugate. Now, you may have seen this in previous classes. Let me show you how or what I'm going to multiply by, and you'll see what happens. I'm going to multiply by the square root of x plus 5 on the top and on the bottom, okay? And the reason that's allowed is what I just wrote in red is really just 1, right? It's 1. So let's see what that looks like when I actually FOIL that out. So on the top, my first term will be x, right, when I multiply that times that. My last term will be minus 25. And then my inner and my outer end up canceling out. All right. And then on the bottom, I'm not going to FOIL it. I'm going to leave it alone so that you can see this cancels with this, leaving me with a 1. All right. So now I can evaluate this limit, no problem. I'm going to do direct substitution. The top is a 1. The bottom, when I put 25 right here, ends up being 5 plus 5. So the limit here is 1/10. Okay, now on this one, again, I am going to do direct substitution. You could even almost do that mentally in your head on this one. If I put a 0 here, my numerator becomes 4/3 minus 4/3. And my denominator becomes 0. It's the indeterminate form. So what I'm going to do is I'm going to fraction bust this complex fraction. Okay, let me explain. This is some heavy-duty algebra. It is something that you may or may not have seen, I'm not sure. But what I'm going to multiply by is the common denominator of every fraction that you see. which is 3 times x plus 3. Okay, now, this that I just wrote in blue is just a very fancy form of 1. And I need to multiply it by this fraction and that fraction and that denominator. So let's see what that looks like once I do some algebra. The first fraction ends up being, let's see, the x plus 3's cancel out, and I multiply, I get 12. Minus, I'm going to put in parentheses, what I get when I multiply here. The 3's cancel, and I'm going to distribute the 4. And then in the denominator, nothing cancels. So I have 3x times x plus 3. Now let me simplify that. So now I've got the limit as x approaches 0. Let's see, if I distribute, my 12s are going to disappear. So negative 4x over 3x times x plus 3. And then this x and this x cancel out. So now when I go to do direct substitution, this limit equals negative 4/9. Okay, now again, as always, direct substitution is your first line of defense, and you do need to show that. All right, and just to give you some practice, I am going to use the correct notation for that. I'm going to do the limit of the top along with the limit of the bottom. Now, when I do direct substitution on the top, the tangent of 0 is 0. When I do the limit on the bottom, plugging 0 into the identity function gives me 0. So that means I'm going to have to rewrite this in some other way. So here's another way to write this. Tangent is sine of x over cosine of x. And if I multiply that by 1 over x, I have this. Those are equivalent. Okay. All right, and then this is going to be some creative algebra, but you're going to have to start getting used to stuff like this. Ask yourself if this that I just wrote is equivalent to the line above it, because it is. And then if I break this apart using the product rule, I now have the limit as x approaches 0 of the sine of x over x times the limit as x approaches 0 of 1 over the cosine of x. This is something that you learned yesterday. We put it into a calculator. You have to have this memorized. That equals 1. And here, when I do direct substitution, the cosine of 0 is 1. And multiplying those together, you get 1. Okay, we're on the last example for today. Let's break this apart using the quotient rule. The limit as x approaches 0 of sine squared of x over the limit as x approaches 0 of x. Sine of 0 is 0. And even if you multiply it times itself, it's still 0 over 0. This is the indeterminate form. So I'm going to rewrite this. I'm rewriting the original problem as sine of x over x times the sine of x. All right, so now I'm going to use the product rule and write that as two separate limits. On this first one, this is one we have memorized, it equals 1. And on this one, direct substitution gives us a 0, and the answer to this problem is 0.